Yeah, okay, welcome back. Yeah, today's I continued chapter 4 the lecture, so that this is a 7th week's lecture. So that until last lecture, so we derived the Lucas-Stevens matrix equation for the beam element. So that today we are going to apply the Lucas-Stevens equation for the beam structure. So I prepared a very simple example. Yeah, we have two element. This is first element are fixed on the wall. Second element is connected with the first element, and last third node are fixed on the ground. So that the whole element has a length of the L, and then maybe the Young's modulus. I don't indicate the exact value of the Young's modulus and cross-section area. I mean the inertial momentum. So that in these cases, I'm going to apply some specific external forces, 1,000 pound, and then the momentum, the 1,000 pound per feet. So and first node fixed on the wall. That means that we are going to have some reaction forces in here, and then some momentum. Yeah, so this is a more momentum 1, and then this point also fixed point. So that in this time, so maybe there are some reaction forces and then some momentum forces. So, but these two full vector is unknown variable, so that we should calculate the reaction forces and reaction momentum. And then in the second point, we only unknown variable is a displacement and rotational angle. So yeah, I'm not sure that you guys memorized the Lucas-Stevens equation of the beam element. Yeah, this beam element has some complex shapes, a complex value. So that please remember the cube and Young's modulus and inertial momentum, and this has some those kind of Lucas-Stevens equation. And first element is connected first node and second node, so that each node has a 2 degree of freedom. First degree of freedom is for the displacement in the y direction, and second is rotational angle, so that each node point has a 2 degree of freedom, so that we have a total 4x1 displacement vector. So in the second element, we also have a 4x1 displacement field, and also same Lucas-Stevens matrix for the beam structure. And then how can we assemble the only second element connected each other, so that we can easily assembled using this way. So those kind of way, so we can easily assemble the two Lucas-Stevens equation into the one global equation. So and then this global Stevens matrix is also singular matrices, so that we should apply the boundary condition. And then in the previous slide, the first node are fixed. That means that rotational movement and displacement is fixed. But in the third point, I mentioned that here. So I thought that this have a same boundary condition like wall, but in here only boundary condition. There are no movement equal to here, but freely rotated in here, so that we have only 3 degree of boundary condition. So we can neglect here this value must be equal to 1, and this must be equal to 0. This must be equal to 0. What is the meaning of this? That indicate that we can remove this line and this first and column and first and rows, and fifth column and fifth row. So we can erase the whole things. By your hand we can finally obtain the 3 by 3 or so v2 pi2 pi 3 degree of freedoms. But in computationally, we changing this part equal to 1 and remaining part equal to 0, so that this also 6 by 6 matrices are equivalent to this 3 by 3 reduced matrices, so that depending on your convenient, so that you can use any method. But in the computationally, this method more easier than, but by your hand, when you calculate it by your hand, so that this reduced matrix is more convenient to use. So anyway, so we can apply those boundary conditions. So the reduced remains in the reduced matrices looks like this, and second nodal point, they apply the 1000 pound, so that in the negative direction, and we applied the 1000 pound per pit in the counterclockwise direction. So that, and then inside the point there are no applied momentum, so that it must be equal to 0. So that although I do not give an exact value of the Young's modulus and other material property, you can easily take inversion. So I don't know the exact value in here. So you guys can obtain this 3 value. After obtaining this 3 value, you can put this value in the previous local stiffness matrices, so that maybe so v2 pi2 0 pi 3, so that, and then we obtaining the remains f1 momentum 1 momentum 3. Maybe these 3s are related to the reaction pulse or reaction momentum, so that you can finally obtain this 3 value either. So yeah, next topic is this distributed load. Yeah, in the previous lecture I slightly mentioned about the distributed pulse. Yeah, so that all beam structure can be we can apply some distributed pulses. Looks like this. However, yeah, when we consider the only single element, yeah, we can only apply some point load at node, and the inside or middle of the element we cannot apply any point distributed load or point load, so that we should changing this distributed load as equivalently same point pulse or point momentum. Yeah, so if you can, you can also use more element. So at that time you can combining some point pulses and point momentum and combination of the point pulse and point momentum. So but today I'm going to give some insight how to make those kind of equivalent pulses and momentum. So yeah, these 2 elements, due to the existence of the distributed pulse, so the total summation of in y direction must be equal to the same. So that distributed pulse, and you multiply this one, this is the total pulses in y direction. So that when you sum these 2 back pulses, that equal to looks like this. This is an equivalent system. However, so this distributed point pulses are not does not apply on the specific nodal point, so that due to they will have some momentum arm, so that these pulses are generated some momentum reaction momentum, so that we should added those kind of momentum, so that after the sum, this momentum, so that this one has a negative sign, this one positive sign, total momentum equal to, yeah, okay, 0. So sorry, yeah, not 0. So that depending on your system, it cannot be equal to 0. So but anyway, so that today I'm going to introduce how to changing from distributed load to the point load and momentum. So that the first way to the equivalent energy method, so that in here, so that, yeah, due to this distributed force, so that we can measure the work, actually work done by energy work done by this distributed load. So that this work done by distributed load, we can say that those kind of way, this is a forces, and then when you multiply the unit lengths, the distributed force per unit length, so that this become forces, and then the movement in y direction, this is equal to the displacement, so that has the same unit of the work. And then we are summed from 0 to L. So this is equivalent, this is a work done by distributed load. And the second case is when after the changing the point load and point momentum, so that we can also calculate it due to this first nodal forces, the work done by is F equal to the movement. In the textbook they use a D variable to the displacement value. However, I indicated I normally use this, means that U, V, W. U is a displacement in the x direction, V is a y displacement, W is a z direction. So that F equal to X, this is a work unit, and then also second nodal point has those kind of way. Yeah, this momentum also can generate some energy or work. So that momentum works can be expressed as the momentum multiplication rotational angle. So that this also be same. So that finally these two energy must be equal each other. So that this is a easy simple way. So yeah, so that we can put some of these two energy must be equal. That in the left hand side for the work done by distributed forces, and right hand side it's work done by the specific nodal force or nodal momentum. So in the previous here, so that we assume that uniform distribution has a distributed forces are uniform, so that we can put some the Wx equal to W some constant value. And then what is the V? In previous slide, previous lecture, we assumed that the vertical displacement is a third order polynomial equation. So V1, pi1, V2, pi2, or we use those kind of equations, or sorry, not U, in here V is a more proper variable. So that, and here, so that this N1 is a shape function of the beam structure, beam element. So that so although they use a different form, so that maybe they use those kind of form in here, so that you can you can put here, so that there are some x variable in here, this is constant, that you can easily integrate it. This is a polynomial integration, so you guys can easily achieve this goal. So after the integration, x3 becomes 4 for x fourth order, and that this part become this one, yeah, this part, yeah, this one. So, and then after then you can add it from to 0 to L, so that all value due to the 0, so that all value equal to 0, then you can only put some the x equal to L variables in here. So after the sorting, finally we obtain those kind of things. Yeah, this is must be same, so that yeah, due to this part is the work done by momentum at the first nodal point. Yeah, this part is a work done by momentum at nodal point 2. So that means that m1 must be equal to w, m2 w equal to this one, f1 is equal to the 2 over L w, f2 equal to this way. So before we start, we assume that this is a f1, this is a f2. Yeah, actually, sorry. Yeah, we say that this is a f1, this is a f2, and then this is a m1. Actually, this is a exact form value, but in here, so they say that f1 has a minus sign, so that this one you should changing the direction, but this become positive value. And then momentum 1, yeah, this is a negative sign, so that you should draw the opposite direction. And then this has a positive sign, so that you can use a counterclockwise direction. Yeah, this is how to changing the equivalent node process. So actually truss element, so that at that time, so that we don't need to do those kind of way. It is because that all truss, yeah, all external forces can be act on the specific node point. So sometimes, so we can so that in the truss element we can also use those kind of generally we apply those kind of forces. However, in truss element we can apply those kind of some distributed forces. Yeah, so at that time you can using those kind of energy approach or work done method. Yeah, so next time I prepared some example to put this one. Yeah, so that anyway, finally we obtain those kind of equivalent node forces. So that yeah, actually yeah, you can obtain this is a basics our stiffness equation. However, due to the existence of the changing of the distributed load to the discretized force, so at that time you should use those kind of relationship. Yeah, so yeah, I think that this is a slightly confusing, but when you practice some exercise problem, you can easily understanding how we should handle the equivalented nodal forces in here. So then let's go to some example 4-6 problem. So that this is a beam structure, Euler beam structure. This is attached on the wall, so that, and then we apply some constant uniform distributed forces in the minus y direction here. So that yeah, we already know that how to changing the equivalent nodal forces looks like this, and this is time. So that we can use we are going to use only single element in here, so that local stiffness matrices and looks like this, and then this is what is this? Sorry, not L, K. Yeah, so that this is K, or sometime U, displacement vector. So and then in here, so that what is the forces vector? Yeah, actually exact forces vector can be expressed and looks like this. Yeah, but this part, there are no reaction forces, so that must be equal to 0, and that must be equal to 0. However, in here, there are some reaction in the y direction, and there are some reaction momentum in here. Then you should use the same things. But due to the existence of the distributed forces, we changed this distributed forces to the equivalent forces, so that at that time you can add it just added forces. However, in the you should carefully check the thing is here, so that this part is due to the boundary condition, these two value equal to 0. So due to the boundary condition, this becomes a unknown variable. I mean that reaction force, or this part, some become reaction momentum, some force, sometime moment here. But so you can calculate some total some forces. So I use some different indexes. We can check after the obtaining this these two element, so that you can matrix multiplication, you can finally obtain some reaction forces. However, in here, this reaction must be equal to this one. However, exact reaction force is this one, not this one. This is a real reaction. However, this force is also can be handled as a reaction forces in the global stiffness equation, so that to obtain the exact reaction forces, so that you should check those kind of relationship. So this value is calculated the first time is unknown, but after the obtaining solution of the displacement, you can multiplication. After the multiplication between the local stiffness equations, or sometimes global stiffness matrices and the displacement vector, so you can finally real reaction forces. This is in the explanation of the previous slide. So anyway, let's check the more detail. After we have some two boundary condition. So fixed in the y displacement and fixed rotational movement in here. So that after the applying boundary condition, maybe those kind of way, we obtain the reduced 2x2 matrices in here. So that in the previous calculation, they are external, actually equivalent forces, and looks like this. And then after taking the inversion, we obtain those kind of some exact solution. After obtaining this solution, you guys can apply. This is a V2 and part2, which calculated in the previous slide. Here. So then after the calculating these two displacement element is equal to 0, so that after the calculating this matrix multiplication, you obtain this is equal to the 2 WL over 2, and then some values looks like this. But let's back into the previous slide. In here, so that these two element is same, these two part. So and then how about this here? This part actually what is this? We can say we can sometimes think about, due to some boundary condition, it can be looks like reaction forces. However, in here, this force includes some reaction and plus external nodal forces, or external nodal forces is equivalent to the nodal force actually. So that finally our real these two value is a summation of I forgot the equivalent nodal forces, minus WL half here. So that this is a real what I want to obtain this solution. So that finally, put some the f1 is equal to the 2 over L plus 2 over L. Finally we obtain those kind of relationship, so that in here, so we obtain those kind of value. So that means that after the obtaining the some reaction or total nodal forces, after the calculating, you should subtract it again your equivalent nodal forces, so that finally you really obtain the what? Reaction forces or momentum, moments. So this is a explanation of this equivalent to the nodal part. So it's not a big deal, so that okay, I can skip more detail. So in here, so that we can compare this to our element FEM solution and exact beam theory solution. So this is some resultant of the beam deflection, so that there are some residual or some error between the beam theory and FEM cases. However, this FEM solution is obtained from the only single element. If the FEM numerical solution has some error, you can easily reduce this error using the more many elements. But in here they directly compared to the beam theory with one single element, so that displacement compared to the other value, displacement shows a very small error, actually small error. It is because that although we use a very simple very lowest length or lowest order displacement variable, however this is a basic Euler beam theory, actually same, so that there are no big difference between the beam theory and actual FEM solution. But however, due to some numerical issues, so that they can generate some difference. So however, momentum, what is the moment? Do you remember this? This is a second derivative of the displacement. So they added one more thing here, maybe, right? So I forgot the detail, but anyway, this momentum is proportional to the second derivative of the vertical displacement with respect to the x. So that means that due to the small error, we generated more large momentum error. So this is a FEM result. Exact beam theory has a more higher order momentum variable field, but due to we use a very low, simple order displacement field, so that we can obtain the very linear equation. It is because V is a third order equation due to the twice derivative. They become the very simple obtain the single linear relationship. And then finally, this vertical direction is proportional to the third derivative of this vertical displacement, so that we can easily expect this become constant, some constant value, so that vertical value equal to 0, equal to constant value, so that there are big error at the each nodal point. So that if you want to reduce those kind of things, so you should use more discretized element. However, you should check the in the beam theory, displacement more exact. However, momentum error is larger than displacement, and then vertical actually forces will have more error than momentum and displacement. This you should memorize this one. So this is an explanation that I already explained here. The displacement has a small, actually small error, but the bending momentum has a more larger error, and shear forces actually has a more large error than, so that to reduce to improve these things, higher order element, so that we don't learn about high order element, but let's skip the detail. This is about the hinge boundary condition, but I don't like hinge boundary condition. You don't need to study this part, so that I also skipped this slide. And then last part is a derivative beam element using the potential energy approach method. So then I'm going to introduce another way to derive the beam stiffness equation. First is a potential energy approach method. The other is Galerkin residual method. However, I don't like the derivative beam element using both methods. So today I'm going to show you briefly. We already know that what is the total potential energy of the solid structure. Although we are going to discuss about beam structure. Beam also solid structure. Total potential energy is a summation of the internal energy and then the external energy, actually work done by external forces. Internal energy in the one-dimensional strain energy is equal to the half of the stress and strain, and the total volume integration looks like this. This is the same. And then external forces is slightly different compared to the truss. In each nodal point has a vertical transverse forces. This T indicates that this Ty, this this T indicates that distributed forces, and then this P indicates that point forces in here. This is the second point, and then this is a momentum. This is a M2, this is a M1. So that actually this is a total work done by the external forces. This is a these two summation of these two terms is a definition of the total potential energy of the elastic beam structure. So to changing this equation, we should know that volume is a beam structure has a constant nearly cross section, and this is a one-dimensional cases. Volume can be expressed and looks like this, and surface is also can be looked like this. So and here you can changing the volume can be changing this one, and then surfaces, and they can be also looks like this, changing this to 1, and then here, so you can combining the point node forces and the momentum work and look like this. And then in the previous slide, although we don't discuss about the shape functions of the beam element structure, but the in V can be expressed looks like this. And then what is the strain? Actually strain is a differentiation of the displacement. Similarly, you can changing this one, so that you can changing this one. That means that this same equivalent to same this one, and this is equivalent to this one. So that how can you say that this one derivative of shape function is equal to the B matrices? So that B matrices in here B1 and B2, B3 and B4. Maybe it is because that in the beam structure shape function has a 4 element. So this beam structure has a maybe the shape function has a 2-order polynomial equation. B matrices become first-order polynomial equation. So anyway, strain can be expressed and looks like this, and the stress is Young's modulus and then strain. And then Young's modulus sometime, yeah, in the, we can use, say that this looks like this, and then strain is in previous slide can expressed minus y and then B matrices and the displacement field, and we can move to the in front, so that finally stress it can be expressed and looks like this. And then yeah, you can edit this stress into here. Yeah, okay, yeah, please remember this one. So yeah, 2 over half and then stress, yeah, y t p u, yeah, this is a stress, and then this is a strain. Yeah, strain is also same form of the, how can we say that, b u. So at this time, so how can you use it? I already mentioned that, yeah, this value is a scalar or matrices or vector. This is a scalar. It is because the energy is a scalar value, so that the last, after the calculating this part, then must become the scalar. So the integration cannot be changing the vector or scalar form. So that inside in the integration equation, it must be equal to scalar. So that to match the scalar value, we should use this kind of transposes matrices. So it is because that after the transposing here, the result also same. So that after the transposing, so we don't have enough spaces. Yeah, I'm going to use it here. So u value in here after the transpose, and b value and b transpose, and d is transpose. However, but this is a Young's modulus or shear modulus, so that yeah, maybe scalar value. So and then this part b and this part u, and then also you can plus y square 2. But this is inside of the internal energy part, so that 2 Young's modulus and I'm not sure where it came from. Yeah, this is equal to the same Young's modulus, and then this y square. So what is the y square? So maybe the y square is a cross-section area that can be changing this I1, so that remaining only integration x is e and half and I, and then in previous slide where it b plus d. Yeah, there are some mistype in here. I think that they need this one. Okay, so and then how about second term? Yeah, this part also can be expressed. Yeah, b is some scalar length, and then t is some distributed forces, and v is some displacement vector. So this v can be changing to the shape function, and then v, yeah, or, and then looks like this. So that, yeah, and then but to obtain the, so yeah, they already use the transposes. It is because after the transpose, this is also same scalar value, so that for the to understand convenient, so that this v become a v transpose, and this n become this part. The w is just constant value in here. So and here, so and then so this part, yeah, actually, yeah, they combining here. So maybe this p include the, yeah, forces and momentum each here, so that this is a different form of the total energy equation. So yeah, and then yeah, each component, yeah, and then to Yeah, this is total potential energy. However, yeah, what is the unknown variable in here? Yeah, actually in here, U is a unknown variable. Depending on the variable U, actually vector U, so that this potential energy can has some value. So that depending on the U, total energy can be increased, sometimes can be decreased. So that, however, in the deformation solid structure, stored internal energy and the substitution work done by energy is how about the I hope that these two energy must become to equilibrium. I mean that total energy when they reached minimum energy value, that is equilibrium of the solid structure due to the stored energy work done by energy. So that to find out the minimum energy, how to find out, there are several ways to check the derivative equal to 0 position. And then if they have several internal variable, how many variable in here, so that we can first variable v1 and the second variable phi1, third variable v2 pi total potential, and last variable is pi2 equal to 0. When this derivative equal to 0, that point we can easily expect the minimum point. So that using those kind of way, so that in the matrix form we can say that this potential can be form V vector form equal to 0. And then in here they have looks like displacement square. So that when you derivative U looks like this, you can obtain the twice and become the displacement U. It looks like okay, so that after the derivative pi p and U here, so that these two looks like a square, so that one square cancel out this one each other. So the remaining thing Young's modulus and inertial momentum, and then one thing is removed, looks like this, and the remaining thing is a B transpose and B matrices, and then this is a U same, and then but it's independent of the function of the X, so that only this part, B matrix only has some variable axis inside in here. So that, and then in here, so that after the derivative U vector, so that they become a constant value, so that remains value are coefficient, and then transposed shape function, and W is a constant uniform distributed forces, and then in here remaining thing is external forces, and looks like this, and then this is reached this equation. But however, in these two terms we can indicate that distributed forces and external load forces is equal to the force, and then in here this part can become the displacement U, and remaining thing is a global stiffness equation. So in this way, what is the K? Young's modulus and sometime L B transpose B dx. This is a local stiffness matrix of the beam element. So that, but normally we can also use it, but no, this actually I already mentioned that what is the general form of those kind of things. In here maybe this is a general form I already told you. So, or sometime integration volume. So that this is some general form of the local stiffness matrix, matrices. It also follows the same result. However, please do not don't forget what is the B? B1, B2, B3, B4, maybe transpose, and then transpose, and then B1, B2, B3, B4, and then maybe 4 by 1 matrices. It is because that normally u, what is the u? n1, n2, n3, n4, and v1, pi1, v2, pi2. This is a shape function and nodal values in here, so that also B matrix is derivative of the shape function and looks like this: 4 by 1 by 4, 4 by 1. So this is a 1 by 1 result. So this part is a 1 by 1. Transposes result is a 4 by 1. So that after the multiplication, total matrix equation 4 by 4 matrices. This is the correct form. So that although I do not prepare the exact value in here, so that how can we use it? What is the n1? Maybe in the previous slide, where is the shape function? Oh, sorry. Oh, I do not prepare the shape function yet, so please check the exact shape function of our beam element, so that after the final calculating, we can obtain those kind of same result. This is a derivative of the beam element using the potential minimum approach method. Next thing is a Galerkin residual method. So to derive the Galerkin residual method, so please remember some fourth order this equation. This is a equation. This is a general partial difference equation. This is a fourth order derivative equation here. So maybe this is a momentum, and that equation came from the momentum equilibrium equation. So anyway, if we have those kind of partial difference equation, you guys can easily apply the Galerkin residual method. To apply the Galerkin residual method, please remember that Galerkin residual method will have some residual, and then summation of the whole domain actually, but we have only single one-dimensional cases, must be equal to 0. But it is hard to achieve this goal, so that we should use some arbitrary functions, and then this function will match it, but in here we use our shape function. So anyway, using those kind of way, so the exact solution, what is the residual? Residual is EI, and then force plus W. This is a exact solution, and then minus numerical solution hat equal to the W is the exact solution, V bar is a numerical solution. Between the two solutions, they will have some error. Actually, this is the exact 0. It is because that they already mentioned that this relationship, so that the remaining residual is equal to looks like this. However, depending on your system, you can switch this here, so that the finally, anyway, the residual R expressed then looks like this. Although they use a V itself, but this V is some numerical solution assume. Exact solution, if the V is exact solution, total inside it must become equal to 0. However, this V is a numerical solution, so that in the whole domain, this solution of the V cannot match equal to the 0. So that to reduce the difference or error, so then we are going to use some Galerkin residual method, so that in here we use some arbitrary function of the shape function in here. So then how can you use it? So in the previous slide, V, what is the V? V is 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 V this that has this form. So yeah, to here, how can we use it? So there are many ways to use it, but yeah, just think about, yeah, V is a third order polynomial equation. When you apply the fourth order derivative in here, yeah, this V automatically become 0. So that, yeah, how, yeah, we have some techniques so that, yeah, what is the integration by part? Yeah, integration by part, you can reduce the order of the derivative. So that how can you apply the, yeah, maybe this part remaining, yeah, here, yeah, derivative value in here. So yeah, you can yeah, sorry, yeah, this part is yeah, you should changing this to switches. I mean that, how can I say that in English? Normally when I apply the integration by part, I say that 그적 미적, so that 그적 미적 means that this, yeah, shape function remaining here, and then this part must be integration one time. So that how can you say that? Yeah, yeah, 그적 minus integration 미적, yeah, yeah, 미적. So yeah, this same here. So this is an integration by part. So yeah, and then yeah, and I and wx. So this become part, maybe you can easily expect it in here, so that it is called the integration part, and looks like this, and the remaining part. So yeah, so we can say that. So yeah, I don't prepare the details so that, but anyway, in this time, so you guys can, I don't have enough spaces, so, but anyway, so in this time, so this part, yeah, this notice is indicated that ni comma x indicated that, yeah, derivative this one, so that xx indicated the second derivative and I. So yeah, keep in mind, I think that, yeah, this is a small subscription maybe, so that due to the yeah slightly difference, it makes me confusing. So but anyway, so anyway, we have a first derivative of shape function here, but also third order polynomial equation has some very high order, so we can we cannot take averages. So that I think that we should apply the integration by part again. So but I don't prepare the detail of the procedure. So anyway, this part, yeah, can be say that looks like this. Finally, yeah, so maybe this part can be reduced until this here. It is because that without the existence of this equation, we cannot obtain this b and u variable in here. So yeah, we should take integration by part at least twice time, so that finally we obtain those kind of relationship. I already mentioned about that this part is some ku part, and then this part can be expressed in some forces part. So this part is due to the distributed forces load, and this part some due to the some external force. This is a shear resistance forces. This is m is a momentum forces. So that these shapes are slightly changed already. So that yeah, you guys can negligible some changings over here. So that anyway, finally we reached some those kind of relationship anyway. So but yeah, here, so the nywxx is equal, can be expressed, yeah, this part can be expressed B transpose, and ei can exist itself, and this part here, so that yeah, this is a reach the local steepness matrix and looks like this. But yeah, I can explain the more detail about the Galerkin residual method for the beam element, but yeah, so I don't think it's important to memorize the. 예, 잠깐 갤럭킨 레지더얼 메소드를 좀 잠깐 자세하게 보려고 했었는데요. 예, 먼저 빔 엘리먼트에서 갤럭킨 레지더얼 메소드까지는 쓰실 필요는 없고요. 사실 좀 중간 과정을 제가 준비를 못 해가지고 좀 설명이 매끄럽진 못했는데, 어쨌거나 이런 미분 방정식이 4차 미분 방정식이 있으면 어쨌거나 수행을 하실 수 있으십니다. 근데 이제 이거를 수행을 하려면 저희가 3차식이다 보니까 인테그레이션 바이 파트를 한번은 분명히 수행을 해주셔야 되는 상황인데요. 예, 뭐 앞에서 뭐 했던 방법 그대로 사실 하시면은 어렵지 않게는 가능은 하십니다. 그래서 그냥 증명을 하시게 되면 이렇게 나오니까요. 그냥 좀 이런 방식이 좀 있구나 해주시고요. 이제 갤럭킨 레지더얼 메소드를 갖고 가는 이유는 뭐 여러분들에게 2D 설명할 때 조금 도움이 돼서 하는 거고요. 어쨌거나 using those kind of way, you can reach we can derive the beam element equation. But so this is today end of the today's lecture. So that using in this chapter we learned about the beam theory. But we are going to use only Euler-Bernoulli beam theory, yeah, in the linear elastic theory. So that please remember how to what is the beam stiffness matrices. So maybe we learned about some potential energy approach method, and slightly briefly introduced the Galerkin residual method for the deriving the beam stiffness matrices. However, most important thing is today is equivalent nodal forces. Yeah, in the 2D and 3D simulation, yeah, maybe this equivalent to nodal forces also used to changing the surface forces, I mean the pressure, to the specific nodal forces. So that this method, please remember how to changing some distributed some pressure to the specific nodal forces. 예, 오늘은 조금 빔 티오리가 다 마무리됐고요. 예, 먼저 기억을 해주셨으면 하는 거는 이제 저희가 이제 2주에 걸쳐서 빔에 대해서 조금 반복을 복습을 좀 해봤고요. 빔 스티프니스 이퀘이션을 증명을 하기 위해서 기본적인 빔 시오리를 가정을 했는데, 사실 조금 제가 빔을 여러분들에게 소개시켜 드리고 싶지는 않은데, 그 이유가 이제 저희가 어떻게 1D, 2D 이렇게 3D 시뮬레이션을 넘어가면서 1D는 사실 저희가 트러스 엘리멘트라고 하는 이제 그런 요소를 쓰고요. 2D는 당연한 거겠지만 뭐 여러분들 아시겠지만 플레인 스트레스랑 플레인 스트레인이라는 가정을 해가지고 하는 스트럭처가 있고, 3D는 그대로 모든 걸 다 이용하는 형태를 띠는데, 빔이라는 구조가 사실은 이런 솔리드 구조랑 조금은 다른 형태를 좀 띠고 있습니다. 그러다 보니까 사실 원디멘셔널 할 때는 사실 이 XX축 방향으로의 변이만을 고려를 해야 되는데, 이게 트랜스버시스랑 로테이션을 갖다가 늘려다 보니까 사실 어떻게 되면은 그 변이장의 함수가 선형이 아니라 비선형 함수를 쓰게 되죠. 3차 함수를 쓰게 되죠. 그러다 보니까 이제 조금 모양이 조금 복잡해지는데, 그러다 보니까 증명하실 때 좀 살짝 모양이 어긋나 가지고 제가 갤럭킨 레지듀얼에서는 좀 자세하게 안 보여드렸는데요. 그쪽을 너무 집착을 하진 마시고요. 기억을 해주셨으면 하는 건, 사실 이제 빔 시오리는 이 흐름에 맞췄을 때는 사실 좀 필요는 없습니다. 근데 제가 빔 시오리를 하는 이유는, 저희가 아마 강의 중간에 조금씩 나왔던 게 뭐 하이 오더 쉐입 펑션 혹은 뭐 엘레멘트라는 말이 좀 나오는데요. 이 하이 오더 쉐입 펑션 혹은 엘레멘트라고 하는 것들이 보시는 것처럼 빔에서는 변이장을 3차로 가정을 했잖아요. 원래는 우리가 변이장을 1차로만 가정해도 충분했고, 사실 수치적인 방법을 쓸 때는 최소한 간단한 방법을 써가지고 풀고자 하는 게 목적이었는데, 여기서는 이제 어쩔 수 없이 3차 빔의 이론을 적합하게 사용하기 위해서 이제 3차를 쓸 수밖에 없었습니다. 근데 이렇게 됐는데, 사실 이 원디 트러스에서도 얘를 2차 혹은 3차로도 늘릴 수가 있습니다. 그게 사실은 이 빔 결과랑 거의 유사하게 나오다 보니까 이 부분도 조금 기억을 해주시면은 나중에 뭔가 하이 오더에 대해서 고차원 요소를 쓰겠다라는 말을 할 때, 이런 뭔가 변환 과정을 좀 거쳤구나, 변이장이 선형 변이장이 아니라 뭔가 복잡한 고차 폴리노미알 이퀘션을 갖는 변이장을 썼구나 라는 것을 조금 기억을 해주시면은 좋지 않을까 라고 생각을 해서 조금 빔을 좀 해봤고요. 사실 이제 빔이 끝났기 때문에 아마 챕터 5는 좀 스킵이 될 것 같고요. 아마 챕터 6로 가서 바로 플레인 스트레스 앤 플레인 스트레인 쪽으로 넘어갈 예정입니다. 그때 이제 아마 어떻게 보면 이제 진짜 이 유한 요소에서 여러 가지 왜 이런 걸 해야 되는지에 대해서, 이제 그리고 여러분들이 인테그레이션 같은 걸 많이 했었는데 그 수치적 분이라든지 혹은 이제 다양한 기법들에 대해서 좀 더 이제 복잡하게 배울 예정이니까요. 먼저 1D 케이스에 대해서 여기까지 잘 못 따라오셨더라도 복습을 꼭 해주셔야지 기말고사 때 문제를 풀 수가 있으시니까요. 혹시 질문 있으시거나 그러시면 언제든지 메일을 보내주시고요. 예, 문의 메일이 거의 없는 것 같습니다. 그래서 여러분들이 잘 따라오고 있는지 안 따라오고 있는지 제가 확인할 길이 없다 보니까 좀 숙제를 조금 왕왕 제출을 해가지고 공지했던 대로 한 숙제가 한 4개 이상은 나갈 예정입니다. 그래서 혹시 기말고사 때 아니더라도 숙제로라도 변별력 가를 수 있게 하고 있으니까요. 꼭 숙제 꼭 풀어봐 주시길 바라겠습니다. 예, this is the end of the today's lecture. So see you next week.